Okay, what I wanted to show you guys first, hey guys, ready? Are we ready? All right, what I wanted to show you first is like, here's looking at that same curve that was in the video, and if you guys can see, as you have more and more rectangles, what happens to your guess? It gets closer because you're not wasting, you're not going above the curve as much or below the curve as much, so you're not doing as much extra or as much underneath. By the time we get to 50 rectangles, it looks pretty close to the actual curve, right? And then if you can imagine if we did like 1,000 rectangles, right? Like they'd be super skinny, but at that point, it would look like, yeah, we're pretty darn close. Does that make sense? So that's where when we were doing the video notes from last night and we did that limit as n goes to infinity, that's saying that we've got like a huge number of rectangles, and as soon as we have a huge number of rectangles, our guess for that area is going to be pretty accurate. And once we get to the point where we say we literally have an infinite amount, then we have the exact answer once we have an infinite amount. Does that kind of make sense? What that's doing? Okay. So for us, we're probably not going to do more than like 5 or 6 or a reasonable amount of those. 12, hopefully not you. But these, when you have a specified amount, that's what a Riemann sum is. It's when you're adding up a bunch of different rectangles together. That's basically what it is. Okay. So adding to your notes, we're still doing an area under a curve. We're just doing some more sample problems. Miles. Miles, you want to put your cheat sheet up there for me? Yeah, perfect. Yeah. Okay, you guys ready? Here is our first example of our continuation of the video notes from last night. So let A for area be the area under f of x equals cos x. On the interval from 0 to b, so those are the x values from 0 to b. Where b is some number between 0 and pi halves. So first, we're going to write this expression for the area as a limit. So that's what we were doing in the video. Write the expression for A as a limit. And if you guys remember, you don't have to write this part out because you do already have it in your notes, but when we write it as a limit, we say the limit as n goes to infinity of delta x, and then we have the summation as I goes from 1 to n of the function with x sub I plugged into it. That was the formula that I gave you at the end of the notes yesterday. And we had a way of finding delta x. The way that we found it is we did the interval, we did b minus a divided by n, and n was the number of rectangles that you were making, or the intervals that you were dividing your curve into. And I equals 1. Yeah. And then xi is whatever we got up here, so it's b minus a over n multiplied by I. Or you could write delta x. I think that's how I wrote it in the video notes last night. I said delta x times I plus the a value. So these are the two things we got to figure out before we're able to write this as a limit. Okay, so first let's figure out our delta x. So we get that when we do b minus a divided by n, and we will actually use the letter n if they don't tell us how many rectangles to make. In this case, they don't. They just say, write the general formula. So we're going to say b minus 0 divided by n. And if you simplify that, that's just b over n. Right? And then the x sub I is whatever we got for this multiplied by I. So that's b over n multiplied by I plus the lower end of our interval, which is 0. And so that gives us bi over n. And once we have these two things, now we're ready to just kind of substitute it in for right here and substitute it in right there, and then we'll be done. We'll have the limit written. So when we write this, this is really just like, can you write the notation? This is not, we're not doing any math right now. We're literally just writing the notation, just the shorthand for how we would do this problem. So we're going to say the limit as n goes to infinity of b divided by n is the summation as I goes from 1 to n. And then the next part is our function, and our function is cos x, evaluated with this expression in it. So cos x is being evaluated by plugging in the bi over n. And that is the answer. That's how you write it as a limit. So we're not calculating anything, we're just doing nasty notation. That's all we're doing.
I don't know how you like plugged it in. Like,
so all I did is I found that delta x and I put it in the front.
how do you get in delta x?
This is how I did it. We said the bigger end minus the smaller end divided by n.
Okay.
And then this one,
There?
what part? These are formulas.
Okay.
So this is like general formula. These are formulas for how we get the pieces, and then this is us actually doing it. Okay. All right. So for part B now, we want to make sure we can actually use this. Yep, there's a part B to this, and part B says approximate the area. So if you guys remember from yesterday, the point of this is it was going to help us find the area under the curve. So that's what this limit is doing, is if we actually go to infinity, we could find the real area underneath the curve. So we're going to approximate the area under the curve. So that means we're not going to have n go to infinity, because that would be hard to draw infinitely many little rectangles. We're going to approximate it for b equals half. Pi halves, sorry, half a pi. Using midpoints. So we're not going to use the right side of the rectangle or the left side of the rectangle. We're going to use the midpoint for the rectangle. And why do you guys think we'd use the midpoint? It's a little more accurate. Using midpoints, and we're going to do 4 subintervals. What do I mean by 4 subintervals? Fourths. It'd be rectangles. 4 rectangles is basically what we're saying here. Okay. So now we can actually plug the numbers in. So up here we said that our delta x was the b value divided by n. And so here, if we're doing this for a specific problem, we're going to say our b value is pi halves and our n is 4. So we're going to say pi halves divided by 4. And what does that equal? Yeah, pi eighths. Pi eighths. So that means that each of our little rectangles is pi eighths wide. Each one. Pi eighths, pi eighths, pi eighths each time. Right? And then the xi, or the number that we are going to be plugging into the function. Pi eighths is not our a, it's how wide the rectangles are. A is the lower end of the boundary, and a we already said was 0. Yeah. So this time they're saying that the interval is from 0 to pi halves. Yeah. And then they're saying since we are doing 4 rectangles, if you take 0 to pi halves and you divide it into 4 pieces, each of those 4 pieces would be 1/8 of a pi wide. 1/8 of a pi, 1/8 of a pi, 1/8 of a pi, 1/8 of a pi. If you add those up, you'd get a half. And then for us to figure out our subintervals, we have pi eighths times I plus 0. And so our actual xi values, we're going to start at 0 because that's the lower end. And then we're going to do pi eighths 2 pi eighths would be pi fourths. 3 pi eighths. And then 4 pi eighths would be pi halves. So we started at 0, and then the pattern was continue adding pi eighths until we get to the end. You guys see how that works? So we just kept adding it. Okay. Now, so they're saying basically that when we do this, we're going to say the midpoint using 4 rectangles, and the width of my rectangle is pi eighths for all of them. Are you guys okay with this notation where we take this out as like a GCF so we don't have to write it every time? Yeah. Is that comfortable? Okay. So then for us to figure out the height of our first rectangle, we have to look at the middle of 0 and pi eighths. What's the middle of 0 and pi eighths? Pi sixteenths. So the height of the first rectangle is going to be cos of pi sixteenths. The height of the second rectangle is going to be halfway between 1/8 and 2. It's not squared because our function here is cos x. Yesterday our function, or last night, our function was x squared, which is why we were squaring it every time. So this time our function is cos x, and so we're going to do cos of the number each time. Okay? Yeah. So when you find the height of your rectangle, you're just taking that x value and plugging it into whatever the curve happens to be, the equation for the curve. Yeah. All right. So we have to look at the number that's halfway between 1/8 and 2/8. What number is halfway between 1/8 and 2/8? It's 3/16 is what's in between. So cos of 3 pi sixteenths. And then we have to find what's halfway between 2/8 and 3/8. You could just add them together and divide by 2. So 2 plus 3 is 5, right? So we have 5/8. 5/8 divided by 2 is 5/16, right? 5/8 divided by 2. Anytime you take a fraction and divide it by something, you just take the bottom of the fraction and you multiply it by that number. So if I have 5/8 and I'm dividing it by 2, 2 times 8 is 16. So 5/16. Mind blown. All right, and then the last one is halfway between 3/8 and 4/8. So again, we just add those together. 3 plus 4 is 7/8. 7/8 divided by 2 to find the middle of it. 7/16. Okay, so if we type this into our calculator, then we are making our best guess about the area using 4 rectangles, which is a small enough amount that we are not going to hate our lives when we type it in. A large enough amount that our answer is going to be somewhat reasonable, although not necessarily completely accurate. So if you guys want to go ahead and type that in, should your calculator be in radians or degrees? Radians. Make sure you're in radians when you type this in. Has anyone gotten it yet? Still typing it?
Is about pi 4.
Is pi 4 is 0.57? You're reasonably close. Not super close. I know. It's not super close, no.
So like, you say like pi 7?
Pi 7 is less close.
Less close?
Less close. Yes, what did you get?
I got 1.006.
Yeah, 1.006 is about what you guys should have gotten.
All I really do was divide pi halves.
Oh, never mind, I'm wrong.
I got a question.
Yeah.
Okay, so now imagine that we do like 2 pi instead of pi half. What do we we count the negative, like how would you do the negative part of that?
What do you mean the negative part?
Like,
You would only have a negative part if you went to the left as well. If you said like, let's find the area from negative pi halves to positive pi halves, then you would have had negative areas.
Pi halves.
Oh, you mean like the little parts that dip beneath? Yeah. So this is kind of the interesting part. Hey guys, Martin had a good question. He asked about if you picture a cosine curve, part of the curve goes above the x-axis and part of the curve goes below the x-axis. So what happens if you do the part of the curve below the x-axis? The answer is you'd have a negative height, right? Your rectangle would have a negative height. They actually call that a negative area. They do. So you could potentially have some positive area and some negative area that like cancel each other out.
So basically, like that area would be zero.
Yeah. And they don't do absolute value of the areas to say all the areas should be positive. They do have some negative areas in there. Yeah, good question. All right, so let's look at another situation. Just we want to make sure that we understand this rectangle business and that we can do the midpoint version of the rectangles, but that we could also do the left point as the height or the right point as the height. So we're going to say given y equals x to the third on the interval -1, 2. So since we have a negative, we're going to have negative widths here because we have part of our curve is going to the left, which when we type it in as our rectangle, if we use a negative value for the number that we're plugging into the function, we're potentially going to have some area here that's negative. So just be prepared for that. All right? So we're going to write the area as a limit first. And then we're going to use use 6 subintervals and right endpoints. And then after that, we're going to use 6 subintervals and left endpoints because we want to be able to compare this process and make sure we can do both of those options. They're very similar. We just want to make sure we're good. Okay. So when we write the limit, the first thing we want to do is find that delta x part. And how do we find delta x? B minus a, so 2 minus -1 over n, and what is our n this time? 6. So what's delta x? 6 subintervals. So 3 over 6, which is 1/2. Okay? And then we also want to do our x sub I, which is going to be 1/2 multiplied by I plus the a value, and our a value is -1, so we're going to put -1 on the end. So now we are ready to write out the formal notation of what we're about to do. And the reason we have that formal notation is so that you don't get stuck. If we had 20 rectangles, you don't have to write 20 things in the parentheses. That's why we have that formal notation. You could just write this and say from 1 to 20 and call it good. Does that make sense why we have that notation? It's because these can be really tedious to write if you have a big number for your rectangles. So we want to have a shortcut way of writing it so we don't have to waste our time. Okay? All right. So here we're going to say the limit as n goes to infinity is what we would want to do if we wanted the exact answer. And we're going to say of 1/2 oh, sorry, 3. Well, we would start. Sorry, we knew that we were about to do 6 subintervals, so we did it with the 6, even though we're not there yet. So what it should have been to start with is we should have said 3 over n because we're pretending that we could do any number of subintervals we wanted. Sorry, I did not notice that. So, because part A, hey guys, listen carefully. Part A, when we write it as a limit, we're going to do it for any value of subintervals, so we don't want to plug 6 in yet. I was just like, yeah, 6 subintervals, we're about to do that, and I wasn't thinking. So we are going to use this, we're just not going to use the 6 just yet. So change your 6 to an n, and this would be 3 over n, and this would be 3 over n, because right now we're still doing the general answer, we're not getting specific yet, so we're not doing 6 yet. We're going to do it in a second.
So it's like a derivative type thing. You're trying to find all pieces.
Yeah, so this is our, and that's the difference between like a general area. The general area looks like a formula usually, and then your actual answer is going to be when you start to plug numbers in. Yeah. So this would be 3 over n, and then we have that summation notation. We're saying I can start with 1 and go to n, so we're taking all the numbers from 0 or from 1 to infinity, and then the function that we're plugging it into is x to the third. So the thing that we're plugging in for x is this x sub I over here, which was 3i over n. If I just take the I and I multiply it, it would go on top of my fraction with the 3. So 3i over n, subtract 1. So that's me writing just the general formula, how you find this every single time. And then after we have this formula written, now we can do B and C where we're doing specific numbers. Okay. So 6 subintervals and the right endpoints. So now we can say our delta x is officially 3 over 6 because now we're actually using those subintervals. This is for part B. And we know that our x sub I was 3 over 6. We can go back and write the 1/2 now. Sorry, my eraser is terrible. I'm just going to scribble that out. So 1/2 I minus 1. So our xi value is going to start where? Negative 1. And then it's going to go up by 1/2.
So negative 1/2.
Negative 1/2. And then it's going to go up by 1/2. 0. Two. Okay.
1, 2, 3, 4, 5, 6, 7.
Yeah, but we're going in between. So in between is, that's one rectangle, that's the second rectangle, third, fourth, fifth, sixth. All right. So how wide is each of our rectangles? 1/2. And we're doing the right endpoints first. So I'm going to say the right endpoints using 6 rectangles. My rectangle is 1/2 of a unit wide. And if we are using the right endpoints and my rectangle goes from -1 to -1/2, and I want the height based off of the right endpoint, then which of these two numbers am I going to plug in? The one on the right, right? So I'm going to say, I'm going to plug -1/2 into the function. So I'm going to say -1/2 to the third. My next rectangle is still 1/2 wide. And what do I plug in to see how tall it is? 0. So 0 to the third. My third rectangle is still 1/2 wide. And I plug in 1/2 to see how tall it is. How about my fourth? Plug in 1. How about my fifth? 3/2. And then last, we're going to plug the 2 in. Okay. Go ahead and start typing. Yeah, it's a lot of typing, right? Not the most fun?
Not the least fun.
Yeah, it could be worse. Could be better, but it could be worse.
Imagine have to actually write like that many equations straight out.
Imagine if we were doing this one, but 20 rectangles instead.
Yeah, LOL. Huh?
That'd be terrible.
We're going to look at I'm like, what's sad?
6.18.
Yeah.
I actually know how to type it in the calculator. Your phone? Yeah.
Now, if you think about it, this first rectangle you're finding the area from, the x value you're plugging in is going to give you a negative height for that, and you actually had a little bit of negative area right here. This one, if your height is 0 cubed, what's the area of your rectangle? 0, right? So the area of this little rectangle right here was 0. The area of this little rectangle right here was actually negative. And then you had all these rectangles over here which are positive. You guys see how that works for our little rectangles? We got a negative area because we're going to have a negative height. So if I did negative 1/2 to the third, that would be negative 1/8.
I get the math, but like, how are you have a negative area?
It's just saying that your area under your curve was underneath the x-axis.
Did I make it?
I can tell you that she says about this negative area.
All right, so part C is asking us to use the left side. So the width of each one is still going to be 1/2, but when you look at that first rectangle, what are you plugging into your function? -1. You're going to plug the left side in. So the first one you're going to plug in is -1. That's your first rectangle. What are you going to plug in for your second rectangle? -1/2, because that's on the left side of it. So here's our second rectangle, but the left side of it is the -1/2. And then for the third one, the left side of it is 0. And the left side of the fourth one is 1/2. And then 1. And then 3/2. Yeah, and please don't type this whole thing in again. You can take the one you just typed and just take out the 2 and put a 1/2 in instead, right? Are you guys seeing that? Most of it's exactly the same. Right? Because the rest of it is the same, right? -1/2, 0, 1/2, 1, 3/2. That's the same. The only difference is this one had 2 to the third in it. This one has -1 to the third in it. Before you type it in, which one's going to have a bigger area? The one that has 2 to the third, because when we put -1/2 to the third, what's going to happen? We got negative area, we're going to drop our area number even lower. Yeah. Okay. So you should be getting a smaller number than we got last time. Yeah, 1.6875. And so can someone clarify what's the reason for our discrepancy? Why are these numbers so far apart? Not necessarily. It depends how the curve goes.
So if the curve was going up the other way.
Yeah, kind of. Because when the curve goes like up like that, then when you do the left side, the left side would be an underestimate. The right side would be over. But if the curve went the other way, yeah, it would switch. Yeah. So primarily the reason is we got that negative area that's canceling out some of our positive area. We have more negative area on the left endpoint 1 than we do on the right endpoint 1, so that's part of the discrepancy. And then we know there's always a discrepancy when you do the left side versus the right side anyway. They're not going to be exactly the same. Yeah. Okay. So how are we feeling about using the rectangles? Not fun. Notation's weird, right? Notation's kind of weird, but do we understand the purpose of the notation? It's not to make you crazy. What's the purpose of the notation?
So you don't have to write them.
So you don't have to write this out every time. Yeah, eventually we want to get comfortable enough with the notation that we don't necessarily have to write this, even though this is like what we're doing. Yeah. All right.